Welcome back. Now I'm going to start section 6 and 7 of chapter 22. Section 6 and 7, which talks about entropy and the second law of thermodynamics. Entropy is a very important concept, very, very fundamental in nature. It's one of my favorite principles and one of my favorite concepts in all of physics. And you can basically explain a lot of physical phenomena by the concept of entropy and the relationship of entropy and the second law of thermodynamics. So the first law of thermodynamics essentially is saying that energy is conserved. So Q into gas is equal to change in internal energy plus the work done by gas. So if you think about it, the first law of thermodynamics is a restatement of the fact that energy cannot be created or destroyed, right? So if you pour in some heat into a gas, where is that heat going? Well, either the gas is doing work or its internal energy is increasing, right? So first law of thermodynamics is saying, first law of thermo is saying that energy cannot be created or destroyed. Energy can't be created or destroyed. So it's a restatement of the conservation of energy. Now, the second law of thermodynamics, which is the law of entropy, is quite a bit different. It's telling us the directionality of the heat flow, the preference of the directionality of heat flow. That's one of the things that it's saying. Why is it that heat naturally flows from a hotter object to a colder object and not naturally from the colder to the hotter, right? An object which is at, let's say, ice cube, let's say at 0 degrees Celsius, right, naturally will melt and then turn into water, and then its natural preference is to rise to the same temperature as room temperature. Now, if you put a bucket of water at room temperature, it won't suddenly by itself get cooler and cooler and then turn into water at 0 and then freeze. You have to put in some work. Okay, so second law of entropy is saying, a second law of thermodynamics is saying, well, there's many different ways to say it. One way is to say that heat flows naturally from a hotter object to a colder. Heat flows naturally from a hotter to colder objects. Okay, so what's other ways of saying the second law of thermodynamics? Well, the other way to say is that objects naturally, systems naturally tend to go to more disorder than to order. If you want to make them go to order, you have to put in some meaningful work into the system. So this is another restatement of the second law. So systems naturally will go to more or disorder, right? Especially closed systems, right? So systems tend to go to more disorder rather than order. Okay? But if you think about it, the Earth itself is a system, but it's not a closed system, right? So through evolution, it did go to more order, right, over time. We produced multi-living cells from single cells, right? It went more and more orderly. But the universe as a whole went to more disorder, right? So something else has to go to disorder in order to create order out of chaos, right? So you could violate the second law of thermodynamics locally, right? Like, for example, a refrigerator can make a system go to order, right? You can put some tray of water there and produce an ice cube. But because the refrigerator is bringing order into the tray of water and producing ice, it's dumping heat in the back of the refrigerator, right? So it's making your kitchen more disorderly because the kitchen is getting hotter. So in order to cause order, somehow you have to create disorder somewhere else, right? So you can say the second law of thermodynamics, this disorder thing, you can say it in multiple ways, right? If you don't take care of your body, you will naturally go to disorder, right? If you want to create order, you have to put in some work and effort, right? You have to exercise, you have to diet, you have to consistently put work and effort to make your body stay in order, right? So what's another way to say the second law of thermodynamics? Well, the restatement of this to say systems tend to go in a direction to increase the disorder. Well, let's identify something as the measure of disorder, and that's entropy. So systems tend to go to the direction of increasing entropy. So entropy will be the measure of disorders. Measure of disorder of a system. So then the second way of saying the second law would be to say systems tend to go in the direction to increase the entropy, right? So increase the entropy, okay? Now, what's other ways to say the second law of thermodynamics? Well, we've already mentioned these, and that is to say you cannot create a 100% efficient engine, right? And you cannot make a refrigerator without putting in work, right? So in other words, you can't make an efficiency of an engine cannot be equal to 100%, which was in the video I explained to you what that means, that you cannot make the temperature of the cold chamber 0, right? Temperature of cold chamber cannot be 0 Kelvin, right? So why? The other way to say it is you have to dump heat to the atmosphere, right? When you're creating a heat engine, right? This is temperature hot, this is temperature cold. You're extracting heat from the a hot reservoir, you're doing work, and then you're dumping heat to the cold reservoir. So the two ways to say this is, if the temperature of the cold reservoir was 0 Kelvin, you could potentially dump no heat to it, right? So it would be 100% efficient engine. So you cannot create a reservoir which is 0 Kelvin, right? And another way to say that is you have to dump heat to the atmosphere, right? So Q cold cannot be 0 joules, right? Well, what's happening? When you're dumping, when the engine is doing some work, producing useful work, right? So let's say the car engine, you're dumping heat to the environment, and that's causing the entropy of the environment to go up, right? So in a sense, by doing work, by getting from point A to point B, which is what the car is doing, it's polluting the environment, which is causing more disorders, right? So you cannot create completely 100% efficient engine without doing what? Systems tend to go to more disorders, right? So there's no way, no matter how efficient your car is, you're going to create disorder in the universe, right? So, and then for the refrigerator, which is the opposite, right? You're doing work in, and then you're dumping heat to the hot reservoir, and you're extracting heat from the cold reservoir, right? So then the refrigerator, the equation was Q hot is equal to work in plus Q cold, right? Well, for the refrigerator, the restatement of the law of entropy would be to say the work in cannot be 0. Work in cannot be 0. In other words, you can't simply extract heat from the cold reservoir and dump heat to the hot reservoir, right? You can't make a water colder by doing no work. So in other words, the coefficient of power cannot be infinity. The coefficient of power cannot be infinity. Okay? So this is one expression of the second law of entropy. Working cannot be 0. In other words, by you doing work, by you making something which is called colder, by you doing work, you are actually causing the entropy of the universe to increase also. Because you have to do work to do something useful, you're creating more entropy. So the fact that working cannot be 0 is another restatement of the fact that systems tend to go to more disorder rather than order, you see? So all these three ways, heat flows naturally from hotter to colder, well, that is the same as this. naturally heat can't go this way without you doing work, you see? But you doing work is increasing the entropy of the universe. So all three are really saying the same thing. So this concept of entropy, which is measuring disorder, is so important that the universe tends to always go in the direction of increasing disorder. So let's define the entropy a little bit more carefully. What is entropy measuring? What else is it measuring? It's measuring uncertainty. It's measuring missing information. So if I don't know a certain piece of information, the more missing information I have about a system, the more entropy that system has. Missing information. Okay? So all three of these are kind of saying the same thing. So systems tend to go naturally in the direction to increase the uncertainty about the state of that system, to increase the missing information about that system, and to increase the disorder of that system, right? So let's give some examples, okay? So in order to understand this a little bit more, we have to define two important thermodynamics concepts, and this comes from a field of physics called statistical mechanics, which is a statistical interpretation of thermodynamics. The macrostate of a system, macrostate is the state that we find the system to us, right, to observation. So what is it called? It's a macroscopic description of the system, such as a gas, such as the pressure of the gas, the volume of the gas, the temperature of the gas. So it's the macroscopic description. Macroscopic description of a system. Okay? Now, microstate, okay? So a microstate of a system is all the possible individual ways for that macrostate to occur. Okay? All the possible individual ways for that macrostate to occur. In statistical mechanics, this is called W. They use the symbol W for the microstates, all the microstates that yield a certain macrostate, right? So they use the equation entropy S, right, which is equal to Boltzmann's constant K times ln of W, right? So the units of entropy are going to be same, okay? And then the value of Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. And then W is the number of ways to create a certain macrostate, right? So for example, let's say I have two dice. This is a simple example, two dice. Now if I told you, okay, let's say I had two dice in my hand and I didn't look, so I have no idea what that macrostate is. But then I opened it up and I saw that the two dice, the sum of the two dice is showing a 2, right? So that means the macrostate is a 2 now. So macrostate is a 2. Now if the macrostate is a 2 and I tell you how many different microstates give the two dice, make the two dice a value to be 2, right? So how many microstates is that? Well, there's only one way to form a 2 on two dice, and that's if one of the dice is a 1, right? And the other one is a 1. So this is the only microstate that produces a total value of 2. So the W will be 1. Okay? So then immediately you will tell me, oh, therefore you must have a 1 and a 1, right? So then W will be 1. So what will the entropy of that system be? Entropy of that system, K ln of 1. So immediately, because there's only one microstate, right, that means the entropy of the system is 0. You already know. 0, that's joules per Kelvin. Okay, now what if I tell you that the dice is showing, a total of 2 dice is showing 3, right? So then what is the macrostate? The macrostate now I'm telling you is a 3, right? Well, how many different ways of producing a 3 are there? Well, one of the dice can be a 2, and the other one has to be a 1, right? And then, or the first dice is a 1, the other one is a 2. So the W is a 2. Well, now, the entropy of the system is more because there's more missing information. You don't know which dice is the 1, which one is the 2, right? And so there is a bit of uncertainty, the state of each dice. So then that means the entropy is K ln of 2, right? Which is equal to whatever that is in terms of number. So the entropy is higher than it would have been if the value was. So this is the entropy for macrostate 2. We can say S2, and this is the entropy for macrostate 3. So it's higher than the entropy for 2. So what's likely to happen, therefore, if you roll 2 dice? Are you more likely to get a 3, or are you more likely to get a 2? Which one is more likely? Well, this is twice more likely than that, because there's 2 ways to get a 3 versus a 2, right? So a 3 is twice more likely to get than a 2, and therefore systems tend to go to more disorder, right? That means the universe prefers more missing information, more higher disorder, more uncertainty, right? Now how about a macrostate of 4? How many ways of getting a 4 are there? Well, one of the dice can be a 3, one of the dice can be a 1, or this one can be a 1, this one can be a 3, right? Or they could both be 2. This one, 3 ways of getting it, 3 times more likely than to get a 2, right? 3 times more likely to get a 2, and then what is the number of macrostates? The number of microstates is a 3, right? So you can kind of think of it as the ratio of the microstates produces the likelihood, right? How much more likelihood? This is 3 over 1, 3 times more likely. 3 over 2, 1.5 times more likely to get a 4 than a 3, right? 1.5 times more likely because it's the ratio of the 2. So then what is the entropy? S4 K ln of 3, right? If you take the ratio of S4 to S3, you're not going to get 1.5. So the ratio of the entropies isn't going to give you the ratio of the likelihood of getting it. Okay, but we can just say that the entropy of getting a 4 is higher than the entropy of getting a 3. So S4 is higher than S3. Okay? So then, okay, so one of the major reasons that they define the entropy as an ln function is because when you take ln of 1, you get 0. That means if there's only one way of getting a certain macro state, then there should be no missing information and the entropy should be 0. So it's kind of, by definition, entropy becomes a logarithmic concept, right? For everything that there's entropy 1, for any macro state for which there's only one microstate, the log of 1 is 0, and it forces entropy to a logarithmic concept. So you could do log base 10 or ln, but they defined it as ln, right? K ln of W. Okay, how about macrostate of 5? Okay, so then we're going to have here 4 and 1. Okay, 1 and 4. 3 and 2. Right? And then 2 and 3. Is that it? So 1 and 4, 4 and 1, 3 and 2, 2 and 3. And that's it. 4 ways of getting it. So W is 4. S5 is equal to K ln of 4. Okay. So then you can say again, this is 4 times more likely than getting a 2. And then if you take the ratio of 4 to 2, getting a 5 is twice more likely than getting a 3, right? And then you can say that the entropy of the 5 is higher than entropy of the 4, right? So then if I continue, macrostate of 6, okay? So then what is that going to be? So you're going to have 5 and 1, 1 and 5, okay? And then you're going to have 3 and 3, 5. So you can see that it's kind of pretty much going up by ones. W is 5, S6 equals K ln of 5. Okay, now what's the most likely one? 7 is the most likely one, right? Because it's kind of in the middle between, the lowest you can get is 2, right? The lowest you can get is a 2, the highest you can get is a 12. So 7 is basically the middle. So if you go 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are the different possible macrostates that could happen. So 2 and 12 are the same likelihood, right? So we could say macrostate of 2 and 12 should be the same. And then 3 and 11 should be the same, right? The macrostate. So the number of microstates should be the same, right? 4 and 10 should be the same, right? And then 5 and 9 should be the same. And then 6 and 8 should be the same, right? And then the highest one is going to be a 7. 6 and 8, and then the 7 is going to be the highest one, right? So let's do the 7 one. Okay, so there should be 6 ways of getting a 7 as we see the pattern. So we can have here 1 and 6, 6 and 1. And then we can have here 2 and 5, 5 and 2, and then 3 and 4, and then 4 and 3, and then that's it basically. So 1, 2, 3, 4, 5, 6. So W is 6. So then the entropy of this is going to be S7 is going to be K ln of 6, right? So that's going to be the highest entropy. Now if we wanted to talk about percentages and what's the likelihood of getting different roles, you can add up all the W's, W for the second microstate, and then add it all the way until W of the 12th. So basically you would do, there's one way of getting 2 and one way of getting 12, so that would be 2 times 1, okay? And then, so these were the different microstates, one way of getting it, but there were 2 of them for 2 and 12. Then a microstate of 2, then you doubled it, microstate of 3, microstate of 4, microstate of 5. But then the microstate of 6, there's only one way of getting it, right? So you just put 6. So then you add all these, you get 36. So overall, when you add up all the microstates, right, there's 36 possible microstates. So then you can say, what are the chances of getting a 7, right? It would be the number of microstates that yield a 7 divided by the total number of microstates for that macrostate, right? So the chances of getting a 7, chances of 7 would be 6 divided by 36, which is 1/6, which is chance, right? So what are the chances of getting a 2? Chance. So then the chances of getting a 3 is going to be 2 over 36 and so on. Now if I add up all those chances of getting all the numbers, it should add up to becoming 100%, right? So that's kind of how you do this. and change it to a percentage and probability, right? But it's very much related to entropy. We can say the entropy of 7 is the highest because the chances of getting a 7 are the most number of ways of getting 7, and it's a state with a higher entropy, right? So then, now let's use a different concept. Let's use a different concept. Imagine we have a box like this, right, with a volume V1 and V2. Now imagine if there are certain molecules of gas here, N molecules, right? Ask, what is the entropy of this gas? It's occupying V1, right? So imagine that this is the second chamber, is V2 is a vacuum, right? So we can say, what is the entropy of the gas that is occupying V1? Well, there is n number of particles, and they can be in any of the states in this volume. They can occupy any corner of that volume, right? So we can say the initial entropy of the gas is n particles times k times ln of V1, right? nk ln V1. Now, what happens when I open a little bit of the separation door, right? If I open that, what's going to happen? Well, the natural tendency is for the gas molecules to start spreading and occupy a total volume, the combination of the two. Let's say V2 is equal to V1. What's going to be the final entropy? The final entropy is going to be nk ln of 2V1, right? That means after you open that little chamber, the gas particles can be in any state, whether in the left and or the right? So the gas has spread, right, to occupy the total volume. Why? Because now there's more uncertainty. You don't know if a certain particle is at this left corner, or on this right top corner, or the bottom right corner. It could be anywhere, right? So that means the missing information, the uncertainty about where a particle is, has increased twofold. Right? So we can say the final entropy is S final. Now the change in entropy is going to be what? nk ln 2V1 minus nk ln V1, right? Change in entropy. So then if I subtract them, what can I do? I can use the law of logs, which says nk ln 2V1 over V1, and then that cancels, and then you get nk ln of 2, right? So that means the entropy has increased. This example is called adiabatic free expansion. Adiabatic free expansion. It's a particular kind of an expansion of a gas adiabatically. The gas is doing no work against the wall, right? It's not like it's pushing a piston, so there's no heat exchange with the environment. It's just naturally expanding itself to occupy a bigger volume, and its entropy is increasing because the missing information is more. The gas particles can be anywhere. So then I'll talk about this. I'll compare this to the entropy increase in a regular adiabatic expansion. A regular adiabatic is different than adiabatic free expansion. In adiabatic free expansion, the gas is doing no work against the piston. It's just freely expanding to occupy a larger volume, right? And the uncertainty about where the gas particle is now larger, okay? So the entropy is naturally increases. Now, if I want to take all that gas particles and squeeze them back in, what's going to happen, right? I have to do a lot of work, and it's very, very hard. You can also tie this concept to a concept of people. You can say there is a room full of people, and they were originally occupying only the left room, right? And all of a sudden, somebody opens this the door, you know, let's say it's slidable door, and now people are starting to occupy this the full space. Maybe you're throwing a party at your house, right? And they used to be at a certain location, then you open the doors and you say, okay guys, the other room is also available, there's food there and stuff. People are gonna start going and mingling and spreading. This is adiabatic free expansion. And then if you're the host, you should say all of a sudden, guys, hold on. This is an example of adiabatic free expansion. The entropy of the house has now increased. Okay, a little bit of a joke. But you can always mix in physics in your real life. Now, if you wanted to get all those people back in here, maybe you want to put a certain slideshow, and now you want to see a birthday, let's say it's a birthday party, you want to see your old videos, right? It's quite a bit of work now to get all these people, squeeze them back in here, maybe close the slides so no one else goes back there, right? Close the sliding doors, get them all back in, and then regroup so to see the slideshow. You got to put in work. It was very easy just to open the sliding door and have them go and occupy the full house, right? So a lot of work to get back in and to watch the slideshow. So this is another way of saying things tend to go to more disorder, more uncertainty, is to say they like to occupy a larger volume, right? The other way to say it was the probabilistic interpretation of the dice, right? You could also do a hand of poker. Which hand of poker is the most likely, right? Which hand of poker is the least likely, right? Which hand of poker is most probable? Well, basically a worthless hand, like maybe a 2, a 7, an 8, an ace, a king. Very, very, we can call those worthless hands. Worthless hands is most probable. Most probable. So that would be kind of like getting 7 on 2 dice, right? So getting 7 on 2 dice. Since getting a 7 on 2 dice is most probable, if you were playing a game of dice, you shouldn't give a lot of money to someone that gets a 7, right? That's most probable. So nature has it that way so that worthless hands are always the ones that most probable. That means they're the ones that have high entropy, right? So worthless hands are high entropy. A lot of ways of getting a worthless hand. So if you're playing a game of 2 dice and giving people money based on what they roll, the one that has high entropy, the 7, you should give them almost no money, right? So that means a worthless hand in 2 dice should be a 7. Now, the least likely one for getting for poker is the royal flush, right? Very, very unlikely to get a royal flush. The entropy is very low. So you see, they did it in a game of poker where the hand that has the least entropy, right, is worth the most. Why? Because nature prefers high entropy. So same thing, if you're playing a game of dice, you should give the most money to someone who got a 2, right? So go give most money for a 2 or a 12, right? Because there's only one way of getting a 2 and one way of getting a 12, right? So you can design a game that way. So roll 2 dice and do it that way. Maybe roll 3 dice, maybe roll 4 dice, maybe roll 5 dice, and give the most money to someone who gets the least likely event, right? And then someone who has a worthless hand in a game of dice would be the ones that have a lot of chance of getting them, right? This volume way is also kind of like a probability way of interpreting. You can say probability of the molecules occupying more space has increased 2-fold. The other way to interpret the entropy is also a heat way, a heat exchange, right? So heat exchange, we can say the change in entropy of a system is equal to the heat into the system divided by the temperature in the system, right? Or we can say delta Q. Delta Q over T, right? So how much heat is coming into the system divided by its temperature. This is a heat way of explaining change in entropy. So now if heat is coming into a gas, what's going to happen, right? Imagine there's a chamber of gas here, right? Heat is coming into the gas, right? So what's going to happen? The molecules of that gas are going to be moving faster and you're not going to know their state. Right? If I take heat away from the gas, they're going to slow down, and it's most likely to know what state they're in. Right? If the molecules start moving faster, well, they can be here, they could be there, they could be there, and they're more agitated. Right? So as the heat is positive, if this is positive, that means the change in entropy is increasing. Right? If Q is positive, then delta S is greater than 0. If Q is negative, then delta S is less than 0. That means you're taking heat away from the gas is cooling, the molecules are slowing. Now there is more information about what their location is, what they are doing, because they're moving slower, right? So this is the heat way of interpreting change in entropy. Now what is the units? Joule is heat divided by Kelvin. Notice we haven't changed the units of the entropy. With the other way, we have entropy is K ln of W. The units of entropy is the same as the units of Boltzmann's constant, joule per Kelvin. With this way of saying it, heat divided by temperature, its units is also joule per Kelvin. Okay, so next I'm going to be doing some examples. I'll do like one example from a probability dice problem, and then I'll do several examples with heat also. And then so you'll see how these can actually fit together and how they can explain a lot of phenomenon in nature. Okay, thank you very much.